let's begin. So on behalf of, I'm Shuhei Ono, a co-chair of the Goldschmidt 2018 Boston, and this is another co-chair, Steve Palmer, my buddy. So on behalf of LOC and local organization committee, science committee, and White Iron Conference, all the theme chairs and conveners, I would like to thank all of you here in this room and those on the way home or having lunch for sharing exciting discoveries and the state of the art in diverse topics in geochemistry. So it is always exciting and such a wonderful way to meet with people who share the same interest. I had such a good time today, or this week. So during the meeting, we received many compliments about the conference, but there may be things that you think we can improve. For example, the venue, how science themes and sessions are organized, or the amount of beer or wine that you consumed or we consumed. So just please let us know. So if you realize Goldschmidt is evolving and we want to keep up with it. And there's a feedback link at the Goldschmidt Boston website. So any constructive feedback will be important to make a better future Goldschmidt. So I want to make it short. So I hope to see you all in Barcelona in 2019. Nos vemos en Barcelona. Then I would like to introduce Helen Williams. She's the organizer for, co-chair for the Barcelona 2019. Thank you.
Hi everybody. Thank you for still being here. I've had a fantastic week. I'm exhausted and I can barely speak, which has nothing to do with the thermal party. And as I was introduced, we all have a great week. We all come and we all share our science with each other. And we've already been planning for the last year the next upcoming Goldschmidt in Barcelona 2019 from the 18th to 23rd of August. I'm really excited about this. We're all excited about it. Barcelona is obviously, it's a beautiful location. It's located between the mountains and the sea. It has a fantastic culture and cuisine. It's also the venue we've carefully selected at a place that we think is ideally suited for your science. It's extremely logistically easy, 20 minutes from the city center, 20 minutes from the airport, 2 minutes from the beach, just saying. And there are extensive accommodation options. And of course, one of the many things that's important about Goldschmidt is, we share our science, but we also share it in a number of different ways, both formally during presentations, during posters, but also socially. And we've already arranged a number of social events, the conference banquet, an informal social specifically targeted at students, early career researchers, as well as numerous ways to integrate your science and your interactions with each other with the culture and the cuisine of Barcelona. But of course, one of the most important things, and it's one of the things that we feel passionate about, is making this conference really accessible. And for that, we are going to really focus on subsidized on-site childcare, as well as student registration rates. And we're also going to provide an extensive early career research and mentorship program. But of course, none of you would come here without the science. The science and you make this meeting. You're the reason why I and many of my colleagues and friends come back year after year. So please consider submitting proposals for sessions and workshops to Barcelona 2019. This will open shortly after this Goldschmidt, so you can already think about this as you're recovering, and the deadline will be the 1st of November of this year. So thank you very much for your time. You're about to hear a fantastic plenary speech, but thank you for your time. And please consider submitting a session and indeed coming to join us in Goldschmidt, Barcelona 2019. Thank you very much.
All right, we made it to Friday. Yay. It was a great week. Before I introduce today's speaker, I'd like to recognize a few people who've given extraordinary amounts of time to make this year's Goldschmidt conference so successful. First, our science committee was led by Tim Lyons and Daniela Rubato, and also included Hagit Afek, Fong Huang, Ann Pearson, Graham Pearson, no relation, Cara Santelli, and Maria Schoenbecker. Together with the theme chairs, they developed the remarkable science program that makes Goldschmidt the most important geochemistry meeting of the year. The local organizing committee included Ethan Baxter, Don Cardes, Catherine Kelly, Andrew Kurtz, and Meredith Hastings, and they put together the field trips, the workshops, the K-12 program, and so much more. And of course, our fabulous conference co-chairs, Shuhei Ono and Steve Parman, worked tirelessly for more than 2 years to make this a great meeting. It really does take a lot of effort to run these conferences. I can attest personally, and I want to thank you. But before I finish with the thanks, we have to acknowledge the incomparable Jackie Story and the crew of White Iron Conferences, especially for getting us back on track after an unexpected fire drill. And we only lost 30 minutes, and it was really remarkable. So on behalf of the Geochemical Society and the EAG, I want to thank you all very much, and let's give everybody a round of applause. Okay, for our final plenary talk of this year's conference, I'm very pleased to introduce my counterpart from the European Association of Geochemistry. Barnard Marty is a professor of geochemistry at the École Nationale Supérieure de Géologie, I'm sorry about my French pronunciation, and at the University of Lyon, and researcher at CRPG-CNRS in Nancy, France. He is interested in the geochemistry and cosmochemistry of volatile elements, notably stable isotopes and noble gases. He has worked on stable isotope variations in the solar system, processes of planet formation, the origins of terrestrial water and other volatiles, the geodynamic cycle of these elements, and the evolution of the atmosphere from the Hadean to the present. Besides mantle geochemistry, Barnard is involved in space missions such as Stardust, Genesis, and Rosetta. He is a past Goldschmidt Conference chair and is currently serving as the president of the EAG. Please join me in welcoming Barnard Marty.
Okay. Good morning, everyone. And we had a great week of science and fun, thanks to Roberta, Steve, Shuhei, White Iron, and so on. So thank you very much for this great week. So yes, my field is about volatile elements, especially the terrestrial one. And one reason why we have it's interesting to study them is because we are here. I mean, without those elements, without the fine-tuning of the mixing of these elements on Earth, there will be no life. And so far, only life has been detected on Earth. It's a very vast subject. It covers a lot of areas, so it would take weeks to explore all the outcome of this. So here I will rather choose to select a few items. First, I will try to convince you that comets contributed a little bit to the atmosphere, but not so much. And second, I will talk about some development we've been doing by analyzing ancient air trapped in Archean rocks. Do I have a timer somewhere? Or no? A timer? No? All right. Okay, so finding gas in is not difficult in the universe. The universe is made of gas, with the solids being only a small fraction of this. So sometimes some cloud of gas just collapse, and a tiny fraction of such a giant molecular clouds is shrinking. It gives rise to, due to the conservation of the angular momentum, it gives rise to a disk with a central star that start to work on. And to make things simple, this is a brief script of the birth of the solar system. you had a protostar, the sun, that started to nuclear reactions, surrounded by a cloud of gas and dust, in which solids started to aggregate to form small planetesimal, and then the planets turned to be either giants, if they were located far away from the sun where they could accumulate the gas that was present, or rocky planets in the inner solar system where the energy was probably too high to really permit the accumulation of gas. This might not be completely true, in fact. But the Earth, the blue planet, is located in the inner part, and presumably, if formed from local material, should be quite dry. And this is the case. The Earth is quite dry, less than 0.1% water. But there is a but on this. What could have happened in the early solar system is that there was a kind of a big mess with the giant planets moving away or around, having orbits that were not stabilized yet. And in that case, they could have triggered the launching of bodies from icy bodies from the cometary disk toward the terrestrial planet zone, or even from the asteroidal belt from the inner solar system. So a priori, it's not possible to decipher really if terrestrial volatiles were supplied by meteorites or by bodies akin of meteorites as we receive them today on Earth for free, or by ice-rich bodies from the outer solar system, like comets. This is a Halley comet depicted on the tapestry of Bayeux in the 11th century. Okay, but we have clues, we have tools. So one of these tools are the stable isotopes, and the D/H ratio, as well as the nitrogen isotope composition, show huge variations among solar system reservoirs and bodies, which permit in some way to try to establish some genetic links. So at first, the protosolar nebula is quite well constrained to be poor in deuterium and poor in nitrogen-15, either by the analysis of giant planet composition or by the solar wind, or directly the analysis of solar wind returned by the Genesis mission. A second reservoir is, I would say, formed by the Earth, Moon, and bulk meteorites. And a third reservoir is rich in deuterium and rich in nitrogen-15, seems to be the cometary ones. Comets are readily analyzed by spectroscopy. So it seems that there is a kind of gradient along the disk that would suggest that, in fact, the Earth and Moon acquired the volatile elements from the inner solar system, where we find asteroids now. But there is a but. You could also think about that what's happened is that you have a mixture of two extreme composition, the protosolar nebula and comets, protosolar nebula which could have been dissolved in magma ocean episodes in Earth. So again, a priori, it's not possible really to distinguish between these possibilities. But now we have some clues about this problem. And they stem from the Rosetta mission. This was the European Space Agency mission with the NASA participation. That was launched more than 10 years ago, 15 years ago. It took 10 years to reach a comet, the comet 67P Churyumov-Gerasimenko. It was a fantastic mission. The rendezvous was in 2014. The spacecraft whirled around the comet during more than 2 years. And finally, it was shut down, not because it was not working, but because of manpower just to continue the mission. There was several instruments on board. A particular interesting one is high-resolution mass spectrometer that was called Rosina, and the PI was Catherine Altweg from the University of Bern, and it was a consortium with more than 30 people involved. So we have been involved in this instrument, and the good thing is that in space you don't need to have a vacuum system. You just have an ion source. You have some gas, the gas expelled by the comet. In the comet, you can readily analyze the isotope elemental composition of gas. And we focused, in our case, on the noble gas because these are quite interesting traces. They are chemically inert. Their electron shell external electron shell is saturated, so they presumably have no chemistry, and they react to physical processes like phase change, nuclear reaction, radioactivity, and so on. And a very interesting one is the xenon. It's a heaviest stable noble gas, and it's particularly interesting. It has a lot of isotopes formed by different star-forming processes. It has also radioactivity products, including the decay of 129 xenon, which decays to 129 iodine, which decay to 129 xenon, with a half-life of 16 million years. So let's have a look now to atmospheric xenon. Xenon we are presently breathing in the atmosphere. And to compare the isotopes, we need to normalize them. So you first normalize to one of the isotopes, in this case 130, and then you renormalize to a known composition, and in this case the solar wind. The solar wind is probably the best proxy we have for the composition of the solar nebula, from which everything started before planetary formation. So this is our reference. And the isotope composition of atmospheric xenon, represented here by the blue dots, is absolutely non-solar. At this scale, it would not be also chondritic, it would not be meteoritic, it's something different. It's enriched in the heavy isotopes, depleted in the light one, with something that resembles to a mass-dependent isotope fractionation. So in that case, you can apply some mass-independent fractionation law to correct for the 4.2% per atomic mass unit fractionation. You obtain this, which resembles quite well to the solar wind. It has an excess in 129, but this is the radioactivity, this is secondary. And then you obtain the pattern of what we believe is the ancestor of atmospheric xenon. That is something that looks very solar for most of isotope, except that you have a deficit in 134 and 136 xenon. And this has been known for 3 decades. Bob Pepin has been pioneering this field with his collaborators. They called this xenon component that you don't find anywhere in the solar system, not in Mars, not in the meteorites, primitive or not. They called it U-xenon, U for Urs, meaning stranger in German, if I remember well. Okay, so this was a problem for several decades. But now we have analyzed the composition of cometary xenon. That was a difficult measurement. The spacecraft has to be about 10 kilometers from the comet, which is 4 kilometers wide. And the flight engineers were not very happy to have a spacecraft so close, because you have a star tracker system that uses stars to keep the position, but you have also a lot of dust, and the star tracker could be burned. But nevertheless, Katrin Altweg is a strong person, and she was convinced that the xenon was important to analyze. So the spacecraft stayed for 3 weeks very close to the comet. The signal was weak, but we could get reasonable statistics on the counting. And it appears that the cometary xenon is remarkable by being rich in 129 xenon and being depleted in 134 and 136 xenon. That's exactly the 2 isotopes, the depletion that we see in the atmosphere. Why there is such a composition? For 129 xenon, we have to think about some pre-solar material. And for the depletion, we have to think of the heavy isotope, we have to think about mixing of nucleosynthetic component different from the bulk solar system, suggesting that part of the cometary ice could be in fact pre-solar, could be from the interstellar medium. Okay, but now we can play a funny game. We can mix up some meteoritic xenon or solar wind xenon, that would be about the same at this scale, and we mix up with cometary xenon until we obtain something that is very close to U-xenon. And the mixture is 20%, about 20% of cometary xenon and 80% of chondritic xenon. It's remarkable that the fit is very good, in fact. And I think we believe, at least, that this is the first time that we have a quantitative tracer indicating that indeed the comet contributed to the Earth and the ocean on Earth. There is also, even the excess of 129 xenon can be reproduced, which also suggests that this excess could be in fact inherited and not a tracer for atmospheric formation. This is another problem. We have been also analyzing, in the lab, David Baker, PhD, with us, has been analyzing lunar anorthosite for xenon. We selected some samples that were irradiated, that has low cosmic ray exposure age to avoid too much contribution for cosmic ray isotopes, produced isotopes. And again, it seems that this xenon in lunar anorthosite seems to be also a little bit depleted in 134 and 136 xenon. In this case, it could be a link to a possible contribution of comets in the early moon. Okay, and now one may ask, that's good, some cometary material is coming to us, but how much do they contribute to the ocean? And it's possible again to make a mass balance because the xenon to water ratio is measured in the comet. We know the value on Earth. It turns out that if you add 20% cometary xenon to Earth, you don't add so much water. Just because the comets are very rich in noble gas, they are trapped in ice, they are quantitatively trapped in ice from the solar nebula or from any reservoirs, but the solids are not rich in noble gas. So adding a little bit of cometary material, you impact the noble gas budget, but you add almost nothing in terms of water. Less than 1% water should be cometary. Everything I'm saying, of course, is based on only one analysis on one comet, but that's what we have now. The mass of comets that were delivered to Earth, extrapolating this composition, would be something like 10 to 22 grams, which is very small as compared to the late Venere. And just now a brief outline of the timing of these events. 0 MA means formation of the solar system. The proto-Earth probably was already surrounded by some gas that might have been dissolved in a magma ocean. We have heard from Sujoi Mukhopadhyay yesterday that we have some solar, neon, and helium in the mantle. But then we started with the accretion, and it was probably wet accretion. Maybe the comet was already here, a different kind of meteorite. We have the lunar impact within the first 100 million years of solar system history, which blow up part of the volatile, and we continued to have some accretion of maybe of comets and some other volatiles. And now I am going to turn to the second part of this talk. Now we are going to be 1,000 million years after start of solar systems formation, when we start to have sample of the atmosphere of the Earth. So the Earth was quite different at that time. The Moon was closer, maybe not close as depicted here. It's artist's view, but it was a different system. And the difference were also on the environment, on the external environment of the Earth. There are two important boundary layers in terms of atmospheric conservation and evolution. One is the exobase, that's the altitude at which the molecule and atoms do not see each other and can readily escape if their mass is low enough. So if you are within the exobase, you are in a convective system. If you are above, species can escape to space. And another one is the magnetosphere, which is created by the dynamo of the Earth. It's a magnetic field that protects the Earth from injection of charged particles like solar wind particles. So this is the situation, the present situation. In the past, it was different because the sun was different. The sun was less energetic. It may seem paradoxical, but it was less energetic because it had less. It was less helium synthesized. At that time, there was less helium in the center, so the rate of nucleosynthetic reaction was lower, and the power radiated by the energy radiated by the sun was fainter than today. So here you have a comparison. In yellow, you have the sun today, the distribution of wavelength of the sun today, and in red, this was 4.4 billion years ago. An interesting, so this is a paradox because there is no evidence that on Earth, the Earth was completely covered by ice. There had been some period of ice, but with the sun, which would be 20 to 30% less energetic, you should have been covered by ice, unless you have something in the atmosphere that prevented this. But another interesting feature here is that in the far UV range, below 150 nanometers, the sun was more active. And the radiation pressure on this range was maybe an order of magnitude higher than today. And this is an important range of wavelengths, because this is where you can ionize, you can dissociate molecule, and you can ionize molecule. So this is an ancient atmosphere, heating by solar UV, will increase, result in a higher exobase, and the magnetic field might have been weaker, in which case you would have a shrinking of the magnetosphere, and charged particles like solar wind could have penetrated much more than today. So we don't know exactly what was the interplay of this process. So again, we cannot decipher directly by modeling, and what we need are samples. And we've been working on this problem in the lab by trying to find some sample of the paleoatmospheres, not proxies, but direct atmospheric composition in Archean rocks, like in North Pole in Pilbara. You need rocks that are not too much metamorphosed, so they can retain volatile elements. And we discovered that, in fact, you can find traces of Archean air in barite, in organic matter, and in fluid inclusion in quartz. So these are hydrothermal quartz. They are formed when a silica-rich fluid precipitates, as they contain fluid inclusions, which are always a mixture between different components, the hydrothermal end member and presumably the ocean water at the time. So what's happened in that case is that when the water is at the surface of the Earth, you have the atmospheric species that are solubilized and according to the Bunsen coefficient. So if you take two atmospheric species, you measure them in water, you can reconstruct what was the ratio in the atmosphere in equilibrium, provided that you have the Bunsen coefficient, which are well known, but depend on temperature. The isotopes, to a first extent, are not fractionated. So by looking to the ocean, water, and member of fluid inclusion, you can reconstruct the composition of the atmosphere at the time. Of course, it's a tricky business. You need to be there is not so much gas. So we use techniques developed for noble gas, static mass spectrometry. So we have detection limits that are very low. And we can also irradiate the sample. That was done with Ray Burgess in Manchester. When you irradiate the sample, for instance, from the thermal neutron could create some argon isotope from chlorine and for potassium. So in a single extraction, you measure the argon isotopes, the xenon isotopes, the nitrogen isotopes too, we developed this, the abundance, plus the chlorine abundance and the potassium abundance. And what you can do is that try to proceed to several extractions by doing sequential crushing or repeating the sample until you get a kind of mixing relationship between the hydrothermal end member and the oceanic end member. So we have been doing this for nitrogen. So these are results from a sample from the Pilbara, and you see there is a quite good relationship indicating that we indeed have a two-component mixing. One is a hydrothermal end member, which is rich in crustal radiogenic argon and in sedimentary nitrogen. And the other one is presumably the Archean seawater end member. To compare, here is the value of the air-saturated water, modern air-saturated water. And we see that, in fact, the Archean seawater end member seems to be quite similar to the air-saturated water, to the modern one. We did it also for barbitons. That was the thesis of Guillaume Avis. So two different areas, not connected. So it's a general phenomenon. It's not a local variations. And again, we obtain a mixing correlation, indicating that in this case, the nitrogen to argon 36 ratio could have been lower than the modern value. Argon 36 is presumably conservative in the atmosphere since long. We know this from isotopes. So the idea is that the nitrogen to argon 36 ratio at that time was equal to or lower than the modern value, meaning that the nitrogen was the partial pressure of nitrogen was at best equal to the modern one, or maybe even lower than the modern one. And this is very consistent with independent studies based on fossilized raindrops in Archean mudstone from some and colleague, and the size of bubble in Archean lavas, which also tend to indicate that the total pressure of the atmosphere, in this case it's not nitrogen, the total pressure was something between 0.5 and 1.1 bar. So if you mix up the two kinds of results, it leaves space to have more CO2 in the atmosphere playing with the boundary, with the arrows. It gives space to have more CO2, and which could, in fact, resolve the faint third paradox. And we also analyze the nitrogen isotopes. Again, this is a mixing diagram. Here is the modern value is ASW again, and the bar on the y-axis show you the values that are seen now in modern crust, in contemporaneous crust and sediments. And all the values so far are within a mixing between this seawater end member and crustal end member, meaning that probably the isotope composition of nitrogen didn't vary with time since at least 3.5 billion years ago. And this is an implication for the fact that the Earth has probably kept the atmosphere. There was probably already a significant protection, maybe a magnetic field, able to protect against escape, which is obviously different in the case of Mars, because on Mars, the nitrogen isotope composition is enriched by a factor by 60% in the atmosphere, because Mars has probably lost a lot of volatile. Now I will come back to our favorite game, atmospheric xenon, or xenon, and we are going to have a look now in terms of evolution through time. We have this mass fractionation. A priori, we don't know where it comes from, so we are going to normalize now, not to the solar wind, but to the atmosphere, that is to the blue point. And this is normalization to the composition of air. So in this diagram, air is flat. Solar wind, these are the orange points, should be, compared to air, enriched in the light element. And Magali Pujol first, and Guillaume Avis then, has been analyzing xenon isotopes in those three inclusions I have shown you. And the result is that the composition are just intermediate between a cosmic end member and modern atmosphere, suggesting that this fractionation that started from the so-called euxenon composition was not completely done 3.5 billion years ago. In other words, the fractionation of atmospheric argon has been a progressive process through time. And so doing that, Guillaume has been working to a lot of, to several samples dated independently. And on the left-hand side, you see some of the, a sample at 3.3 billion years. And on the right-hand side, you see the evolution of the fractionation. The y-axis is the fractionation per atomic mass unit of xenon in the atmosphere through time. And we see a nice evolution, like this, which seems to end up around 2 billion years. This means that we started with a chemical end member, euxenon. We get to modern xenon about 2 billion years ago. the question, of course, is why what is the cause of this evolution? In passing, I would like also to show you that, to convince you that these are old samples because, for instance, they show a deficit in 129 xenon, which is due to the fact that 129 xenon has also been degassed from the mantle through time. So at that time, there was less 129 mantle 129 xenon degassed at the time. Remarkably also, the other noble gases are not fractionated. We have seen that nitrogen is not fractionated, krypton is not isotopically fractionated, argon is not, neon is not. So that's something that is really specific to xenon. So we've been thinking, just in passing also, xenon is the second atmospheric element after sulfur to show isotopy variation in the distant past. Of course, the cause of this variation are different, but it seems that we have something that evolved through the Hadean and the Archean, and they stabilized around 2 billion years ago. For xenon, we don't know exactly if this is the Archean Proterozoic transition. Maybe it should not, or it could be also linked to oxygen. We don't know this. Okay, so you need to escape xenon preferentially. You need preferential ionization of xenon because xenon, in fact, has a first ionization potential, which is the lowest among noble gas, but also it's lower than N2 or CO or CO2. We know that the far UV flux from the young sun was more intense than now, so this is good. Xenon could have been trapped in organic haze, organic aerosol, if there was some stage 4. It is a good way to fractionate xenon isotopes. But nevertheless, you need to get rid of xenon, so you need to lose xenon. And one way that was proposed by Kevin Zandler is that xenon, once ionized, xenon is lifted by escaping ionized hydrogen until the exobase is still stays ionized, and then it can follow the magnetic field line. There are many open questions. We are not sure about the process. They could have a strong implication. There is a potential to trace the interaction between the sun and the terrestrial atmosphere. We don't know if this is a continuous process or if there was some solar flare-like process. And all these are open questions. Some application of this. The first one is now is provide a mean to date directly organic matter. David Baker and Michael Broadley in the lab has found that organic matter, kerogen separated from Archean rocks, are full of atmospheric gas from that time. So they have taken quartzite, a 3 gigayears old quartzite, separated the organics, and analyzed xenon in these organics, and found that it is just on the evolution line, giving a xenon model age of about 3 gigayears, which is contemporaneous to the age of the formation. So this means that it demonstrates the syngenetic origin of ancient organic matter. It provides a mean to date independently organics through time, and we are going to work on this. And David is giving a talk this afternoon, so please go to see his talk. And another interesting outcome of this evolution is that xenon in the mantle is mostly atmospheric, mostly modern atmosphere. About 90% of xenon in the mantle looks like xenon in the modern atmosphere. Only 10% about looks like chondritic. This means that if xenon is recycled in the mantle, or the best way to put atmospheric xenon in the mantle is by recycling, this has been shown notably by the group of Manchester, this means that you have to recycle when xenon was already stabilized to the composition, to the present-day composition. This means, in other words, that it requires xenon recycling less than 2 gigayears ago. And so this is a picture of how it could work. This was published by Guillaume also last year. So during the first time of the Earth's history, you degas xenon into the atmosphere. But then you need to regas to inject xenon into the mantle. And Parai and Mukhopadhyay last week published a nice paper in Nature where they developed detailed model of this. They included other traces, they included water, and they concluded, in fact, yes, that during the first half of Earth's history, volatiles were degassing from the mantle until subduction was able to replenish the mantle with surface volatile, probably or possibly linked to the growth of the continent and or to the thermal state of the subduction that became cool enough to inject volatile. And just to finish, I would like to mention also that we have attempted to determine the salinity of the Archean Ocean. Again, it's the same story. We analyze several times a sample, we step crush until we get a linear correlation, mixing correlation. So again, we have, in that case, this is chlorine over argon-36 versus potassium over argon-36. We use argon as a conservative tracers, and we see again a mixture that we interpret as being between a hydrothermal end member, rich in the crystal, sorry, it should be potassium and chlorine, and the Archean seawater. And then this mixing intercepts the possible space of composition based on modern seawater. And it depends on temperature. It depends also on the salinity. And the conclusion is that this correlation points to a salinity that was comparable to the modern one, with temperature in the range 20 to 40 degrees C. It doesn't necessarily mean that the ocean were at a mean temperature of 20 to 40 degrees C, because this is the temperature of equilibrium, so it's the temperature of the surface. But we think that the constraint on the salinity is quite robust. The slope of the correlation gives you the chlorine to potassium ratio for Archean seawater, which turned to be 50, higher than the modern one, which means that if chlorine was the same as today, potassium has to be less abundant by 30 to 40%, which could be also related to the continental crust growth. Okay, so we have finished this brief travel into the deep time. So the ancient atmosphere was significantly different. No or little oxygen, we presumably from S isotopes. The salinity of the Archean Ocean was comparable to the modern one, but less potassium, probably lower partial pressure of nitrogen, which could leave space for more CO2, and so resolving the faint paradox. No nitrogen escape, efficient shielding from at least 3.5 billion years, which is consistent with already an active dynamo at the time, which is indicated independently by paleomagnetic measurements. Xenon escaped, probably because of this electronic structure, interaction with far UVs. It could be, well, it seems to be a new chronological traces, if you find some SAMs that escaped the atmosphere from the time. And efficient recycling started just around 2 billion years ago. So I think we are just beginning to explore the environment of the cradle of life. And of course, this is a group effort. And I would like to mention all the students and postdocs that have been working on this problem. You see them here: Eric, Laurette, Magali, David, Antonio, Michael, Pete, Guillaume, Evelyn, and so on. And also the scientists who have been exchanging, the Rosina team, Nick Arndt, Ray Burgess, Axel Hoffman, Pascal Philippot. These are the Archean guys. And we were founded mostly by CNES, the Deep Carbon Observatory, and the European Research Council. Thank you very much for your attention.
That was a fascinating talk. Do we have questions? And if we do, please come to the microphones. There's one in the front and one in the back. But I will kick us off with a question, which is, what is special about xenon relative to krypton or neon, et cetera, and that it can escape? It's so heavy.
It might be a combination of factors. First, xenon ionizes much easier than other noble gas. Then it is possible that the far UV distribution of wavelengths was specifically favorable to xenon, because it's quite variable, the distribution of wavelengths. And in fact, it could be the case because on Mars also we see some fractionated xenon and not krypton. It seems that we have a similar problem or process, and which could be explained not by, I would say, tectonic origin, but by external origin, like interaction with the sun.
Question? Go ahead.
I'm very interested by the fact that you have such a potential depletion of the potassium at that age, because that fits very well with the fact that we have, during the alteration of the basalt, especially in the barberton, and especially during the silicification of the top of the basalt, we have a large enrichment in potassium associated with the silicification. That's just a comment.
Okay, I take it.
And I have another question, which is well, you have to go to the microphone, and then I'll call upon you. The Rosetta findings are fantastic, but do we know how do we know that all comets are the same?
Well, the Rosetta mission costed something like 1.3 billion. So if you have 1.3 billion more, we can go to another comet. Yeah, we would love to have more data, but we do with what we have. We have to rely on the early measurement.
Eric.
Cool. I don't know why I have to walk to the back of the room to ask a question. My question is probably really naive, okay, and my understanding of the early atmosphere is really rudimentary, but I've seen a large number of arguments on why it's ammonia and not nitrogen. Do you know what the form of the nitrogen is in the atmosphere and why?
Well, I would think that it's N2, because we analyze as N2. That's a good reason for. And the partial pressure of the nitrogen to argon ratio is consistent with the modern one, also a little bit different and lower.
Yes?
Hey, Barnard, fantastic talk. You're arguing that the early atmosphere had a lower nitrogen content than today, but we also know that the continental crust, which can contain between 0.2 and 0.5% of an atmosphere of nitrogen, has been growing over time. So where is all of this extra nitrogen coming from?
Yeah, this is in fact a shocking result. We would have expected to have more nitrogen in the atmosphere, especially because if we believe that subduction was not so active at the time, a good way to sequestrate nitrogen is to recycle silicates where nitrogen substitute to NH4 to potassium. But this is a result, and so we have to find another way. I think we have to find other processes that is able to answer this problem. In fact, this lower than today nitrogen pressure is consistent with the work done on the partial pressure of the atmosphere at the time by the group of Sohm and colleagues. We have to find.
Another question?
Yes. Maybe that's also naive, but could we use the Pilbara fluid inclusions and others to say something directly on CO2 content of the ancient atmosphere?
That would be great, but fortunately CO2 is quite reactive. Nitrogen and noble gas work because they are quite inert. N2 is a very solid molecule, but CO2 I think is too reactive during the hydrothermal process to be kept, to be conserved. But that would be great, obviously.
So I'll close us with one piece of information that's related to all of this, which is that NASA is considering a proposal. It's been down-selected for a mission to the same comet visited by Rosetta to return samples. And if that gets funded and if all goes well, we may have some ground truthing of the results from the spacecraft, which would be really, really neat. So let's thank Barnard again for a great talk, and we'll go to lunch. Thank you.
problem is the timing of the mission for me.
Yeah, I know, right? Steve Squires, who
Yeah.
gave a presentation to our